All right, everybody, welcome back. We are here in our first video of section 10.14 of AP Calculus BC, finding Taylor or Maclaurin series for a function. Just a few sections ago, we discussed the process of how we find Taylor and Maclaurin polynomials and how we use them to approximate the values of the function. What we're going to do here is we're going to take the same idea, the same generating idea for making those polynomials, only we're going to turn those into infinite series, power series. And we kind of hinted at this in the last lesson when we were talking about, the remainder, Taylor's theorem with remainder. Was that the last lesson? 2 lessons ago when we talked about Lagrange error bound, and last lesson when we were talking about finding intervals of convergence, we hinted upon the idea of extending these polynomials into the infinite power series. The thing about these infinite series is that when we look at them on their interval of convergence, they are actually equivalent to the function. Okay, and it's going to be important for us when we talk about a power series. It's going to be important for us to know their interval of convergence because that's where the series and the function are going to be equivalent to one another. All right. In the box here, you see the general format for a Taylor series generated by a function at x equals a, and you've seen this before. It might not have been written exactly like this because I've actually extended it so that we're unified in our structure, that we've got f of a over 0 factorial times x minus a to the 0, kind of being just more meticulous with our definition. But in essence, this is the important key thing for us to look at right here. This represents the series. It's the sum from 0 to infinity of the kth derivative at a over k factorial times the quantity x minus a to the k. That's the Taylor series at x equals a. If we want to talk about the Maclaurin series, the Maclaurin would be the sum from k equals 0 to infinity of the kth derivative at 0 all over k factorial times x to the k. And that's the summation notation for the Maclaurin series. That's a little wonky there, but you can see that's the kth derivative. All right. In general, if we're trying to represent these series, what we're going to do is we're going to write the first several terms, usually 3 or 4. On your AP exam, they'll usually say, write the first 3 terms and the general term. But mainly when we're writing these series, we want to write the first 3 terms and the general term, unless they ask us for something different. All right. Now, one of the things that we're going to do, we know how to generate these series already. We're going to use the same ideas that we used when generating the polynomials. We'll have the 0th term and the first term and the second term and the third term, and how we generate all of those. And then we can generate the kth term in the same way. Can figure out what the kth derivative is at a divided by k factorial times x minus a to the k, and that's going to be our general term. Okay, but we'll see that more when we do a couple of these later on in the lesson. But before we do that, one of the nicest things for us to do, and it's going to be our focus of some of this lesson and some of the next lesson as well, is to take well-known series and use those to be able to write infinite series for other functions. So over the next couple of pages here, we're going to dig into some of the common Maclaurin series that it's good for you to know. And I'm going to break them down into 3 categories as we talk about them. So let's go ahead and we'll look at some common Maclaurin series that every good calculus student should know. Group 1, Maclaurin series that you absolutely must know for your AP exam. These are the 3 series that you are required to know. They might ask you to use these series in context on your AP exam, and you absolutely must know them for your AP exam. The first one is the series for e to the x. Our function here is e to the x. Here's the Maclaurin series for e to the x. And the interval of convergence for this series is all real numbers. In fact, all the series that we absolutely must know for our AP exam have an interval of convergence of all real numbers. Now let's take a look at what this looks like, this function, compared to the series. So I'm going to go over here to our graph screen, and I'm going to go ahead and graph y equals e to the x. And I'm going to shift my window here so that I can see this a little bit better. All right, there's the exponential function. Now, if I go back and I look at this infinite series, it's the sum from 0 to infinity of x to the n over n factorial. If I add terms to this successively, it should look more and more like this function because the interval of convergence is from negative infinity to infinity. And every term that I add to this series, it will get closer and closer to the function for all real numbers. So let's start by just the first term, y equals 1. All right. When I use just the first term, it just gives me, boom, it's equal to the function at that point. So let's add the next one, 1 plus x. Now we've got a little bit wider of an interval that's covered by this line. Okay, if I zoom in really close, you can see that that line's really close for, you know, a decent stretch, not a huge amount, but maybe from negative 0.1 to 0.1. It does a good job of approximating the function. But as I add each successive term, let's add x squared over 2 factorial, x squared over 2 factorial, which is 2. You see that this covers up more of the curve. And if I add the next term, x to the third, over 3 factorial, which is 6, you see it covers a little bit more of the exponential curve. And if I add the next term, x to the fourth over 4 factorial, I keep doing that, I forget to. You see that it covers even more. Look at how good of a job this is doing over to the right-hand side of the origin, how close it is to covering that curve already with just 4 terms. It's pretty darn close to the exponential function. And as I add additional terms, x to the fifth over 5 factorial, which is 120, look at that. And x to the sixth over 6 factorial, and you see how good of a job this, look at that. Look at how close it is to the exponential curve. You know, for a very good chunk of this curve. And if I continue adding terms to this, it's just going to widen that interval where the curve and the series, where the function and the series are identical to one another or close to identical to one another. And when we add an infinite number of terms, this polynomial and this function are going to be the exact same for all real numbers from negative infinity to infinity. So that's the first Maclaurin series that we absolutely must know for our AP exam. The second one and the third one that we must know sine of x is x minus x cubed over 3 factorial plus x to the fifth over 5 factorial. We've seen this already before. We generated a polynomial for sine of x in the past. We generated a polynomial for cosine of x in the past, but these are the series forms for sine of x and cosine of x. Both of these converge to the function for all real numbers. And if you look at, let's do exactly what we did with e to the x, except with the sine of x curve. We've got y equals sine of x. All right, so there's our sine curve. And we're going to go ahead and add term by term. The first term is x. All right, so we're going to have y equals x. And you see how closely y equals x looks to this curve, very close to 0, but then it falls away. And as we add more terms, we're going to add minus x to the third over 3 factorial. And it covers more of that curve. And then plus x to the fifth, I guess I can use the exclamation point, over 5 factorial. And then we add the next term, minus x to the seventh over 7 factorial. And you'll notice that as we add these terms, we're stretching out further and further along this curve the amount of curve that is covered by the polynomial approximation. And minus x to the 11th over 11 factorial, and plus x to the 13th over 13 factorial. And look at that. I've almost covered the sine curve from like about -5 to 5. This polynomial matches the sine curve exactly. And as we keep adding terms, this is going to pinch closer and closer to it. When we have an infinite number of terms, they'll be exactly the same. Of course, we technically can never actually get to an infinite number of terms. All right, at least not. I can't write out an infinite number of terms, and I can't graph an infinite number of terms. But conceptually, we can understand what it looks like with an infinite number of terms. And then the cosine curve, same thing. I'm not going to go through what I did with the e to the x and the sine of x, but those are the three that you absolutely must know. Okay, so make sure you know those. Group number 2, Maclaurin series that you should probably know, but can figure out pretty easily. The Maclaurin series for the function 1 over 1 minus x and 1 over 1 plus x. These both come from the concept of these are geometric series, and their interval of convergence here is from -1 to 1. But both of these come from the a over 1 minus r formula. You know, if we look at a geometric series, the sum is equal to a over 1 minus r. So when I look at 1 over 1 minus x, that's a series with a equals 1 and r equals x. So as long as the absolute value of x is less than 1, this converges. That's where that interval of convergence comes from. And so this is the series a plus ar plus ar squared, etc., etc. And so I can just jot these terms out. A is 1, a times r is x, a times r squared is x squared, a times r cubed is x cubed. So if you think about these this way, you don't necessarily have to remember them. You can generate both of these series pretty quickly and pretty easily. Okay, now let's look at the first one and compare it to its interval of convergence on our graph and see what happens when we do that. So we're gonna look at 1 over the quantity 1 minus x. All right, here's the function. And we're looking for it to converge from -1 to 1 is our interval of convergence. All right, so y equals 1 plus x. Notice the interval from -1 to 1 is all on this portion of this curve. There's an asymptote at 1 in the original, so we're not actually on that curve. And if I keep adding terms to this, plus x squared, plus x cubed, and if I just look at this from -1 to 1, we're getting more and more of the curve between -1 and 1. Outside of that interval, this is absolutely worthless. This polynomial is absolutely worthless for approximating this function outside of that interval from -1 to 1. But as we add more and more terms from -1 to 1, it gets to be a better and better approximation of this function, and it actually, on the interval of convergence from -1 to 1, becomes identical to the function as we add more and more terms. And I can do the same thing with 1 over 1 plus x. In this case, a is 1, r is -x, and so as I write out a plus ar squared, it's 1 plus 1 times -x, which gives us this minus x, plus 1 times -x squared, which gives us the x squared, etc., etc., to get this series. So 3 Maclaurin series that we absolutely must know: y equals e to the x, y equals sine of x, y equals cosine of x. 2 Maclaurin series that we probably should know: 1 over 1 minus x and 1 over 1 plus x. We're going to continue in the next video with 2 more series that I say, hey, it might be helpful, but you probably don't need to know them. At least not for your AP exam, and I don't know that you're going to get any help from them knowing them on your AP exam, but they're nice to know. We will start with that, group 3, in the second video on this lesson when we come back next time. Have a great rest of your day, everybody. We've reached the end of our first video on section 10.14. Enjoy yourself, and until we meet again, see you later. Bye-bye.